Hey guys, I'm back with a new video. In this video, we'll implement the KNN algorithm on our same iris dataset that we had discussed in the previous video. Now this is the 17th video of our machine learning series. In case you haven't watched the previous videos yet, do watch them first. If you are new to the channel, don't forget to subscribe and like the video. Now I've already discussed this dataset in the previous video, so without wasting any time, let us dive into the code and implement the KNN algorithm on our dataset from scratch. So I'm back in my Visual Studio Code. First, let us import the required packages. So importing the required packages. Import CSV, import random, then import numpy as np, then from scipy import stats. So let us define a function for data input operation for your CSV file. So the function will have following parameters. It will take on the name of the file, which is the path of the CSV file on the system, then the number of columns that are present in our CSV file. As a default value, I will be passing 5, and this will return as a list that comprises of a list of all the input variable values, the list of output values, the list of means for all the input variables, and the list of standard deviation for all the input variables. So first let us define our read data function. To read our dataset CSV file, this will take on two parameters. Now one is the file path, which is the path of the CSV file on the system. Second is NOC, which is the number of columns present in our CSV file. Let us set it as a default argument, so I will give it a value of 5. So if the caller of the function doesn't pass any value from outside, a default value of 5 will be used for NOC. Otherwise, it will get overridden by the new value. So now let us get the file handle for our CSV file by opening the file pointed to by this file path in the read mode. So I can say file object open function, and here we will pass on the file path and use the read mode. Now this will spit out a file instance, or you can say a file handle, using which we will be able to access and manipulate the contents of our file if required. Next, let us define a list of headers, and this will contain the header names, or you can say the column names for each column, which you can see in our dataset we are not having the headers. So we will define a list of headers, and this will contain the header names, or you can say the column names for each column. So I'll create a new variable headers and set that to an empty list. Now if there are no header names in our dataset, which in this case is definitely true because we are not having headers in our iris.csv file, we can create a boolean variable has headers and set that to false as the initial value. So now let us define our predictors collection. As we know, we have 4 predictors in our dataset, namely the sepal length, sepal width, petal length, and petal width. Here we are interested in getting the predictors, which in our case is the first 4 columns. So to collect that, I can say I will define a variable x, and I want 4 empty lists, and I can basically make use of the list comprehension and say NOC minus 1. So NOC minus 1 will resolve to 4, and we will get 4 empty lists inside our outer list, because this will run 4 times for NOC 5 as a default value. So here we will have 4 empty lists within our x variable. Now let us define an empty list for our output response variable or the target variable. So you can say this y as an empty list. Next, let us set up our CSV Reader on the file handle, and this will enable us to read the dataset row by row. So I can say reader csv.reader and pass on the file object to the reader method. Now using a for loop over our dataset pointed to by the reader object that we just initialized, we will be able to read our dataset one row at a time. So I can say for row in reader. Now first, let us check whether we do have header names in our dataset or not. That is, whether we do have a header row or not. So if has headers is true, that is, we do have one. Then I need to collect my headers. So for I in range 0 NOC, from the first row, for which has headers is set to true, we will collect all the header names from that current row, which is the first row, because generally the headers are present in the very first row for any dataset. We can collect them by saying headers dot append, and then we will collect the header from the current row, which we can access by saying, so the current row is marked by this row temporary variable, and to access the location, or you can say the cell in which the header is specified, I can say row I. So we'll first collect the first header name, then we'll move to the current row's second column, and from that cell we can collect the second header, then the third header, which is in the current row third column, and then the current row fourth column will give us the fourth header. Otherwise, if we don't have headers, this will be false. Now right outside the for loop, now once we have collected all the header names, we can set the has headers boolean to false. And right after that, we'll move to the next row of our dataset. And now take the case if our dataset is headerless, that is, it doesn't contain any header row. Then in that case, what we will do is, we'll collect the values of sepal length, sepal width, petal length and petal width by extracting their values from our input variables. So I can say, for I in range 0, NOC minus 1, and then let us append these input variables to our predictors collection. So I can say xi, and then we can append the current row's cell, which is pointed to by index I. So what will happen in this case is that we are focusing on these four values, these ones, and what it will do is, for I is 0, it will say x of 0, which is represented by the first list of our list. So we will take on the first list within this x variable, and in that we will append the current row's first cell, which is pointed to by index 0, which is 5.1. And then what will happen is I will get incremented by 1, then I will be 1, and then we will point to the second column and we'll collect this value, which is represented by a row of 1. So the current row's second value, row 1, and then we will append that to our second list in our x variable, and so on. So the first column values will go in x0, the second column value will go in x of 1, the third column value will go in x of 2, the fourth column value will go in x of 3, and finally this entire x variable, or the list of lists, will get completely populated with our predictors. Let us come outside our else block and within our outer for loop. So now in order to get the list of the response variables, I can say y.append, so row and NOC minus 1, which will be row 4. So for the current row, I want row, and this is 4. So row 4 points to the fifth value of the current row, which is this one. Then we move to the second row, we'll collect this value and add that to our y response variable, which is a list. We'll collect the complete fifth column using this outer for loop, because we are iterating over the entire dataset row by row, and we are collecting our predictors and our response variables, and we are appending them in respective variables, right? So now once this operation is done, which means that this entire for loop is done, we'll have the entire predictors collection for our dataset and the entire response variable collection, which is this final column, in our x and y variables respectively. So now we have our predictors collection and the list of response variables for the entire dataset. Let us now close the file in order to prevent memory leaks, so that our file handles memory allocation gets released. So right outside the for loop, I'll close the file by saying file object dot close. Now let us define a boolean variable, and I will name it as want to normalize, And if it is set to true, then we want to normalize that data. Otherwise, we can set it to false. Want to normalize. Set that to true. Now let us check for that. If we do want to normalize, then what I will do is I will define two variables. So the first one is mean, which will be a list to hold the mean values for each of the predictors of our dataset. So we will be holding the mean values for each of our columns, for each of our predictor columns, which are these 4 columns. So for that I can define a mean variable, set that to an empty list, and then let us define a variable std, which will hold the standard deviation values for each of the predictor columns of our dataset. So set that to an empty list as well. Now for all the input variables or predictors, let us compute the mean and standard deviation. Let us grab each of our predictor columns and compute the mean and standard deviation for them. So I can say for I in range 0 number of columns -1. So I'll start from the 0th column and move till the last predictor column, and then to refer a column I can say x of I. So this for the very first iteration will be the first column, x of 0, and let us transform this to a numpy array. Then to get the mean for the very first predictor column I can say np.mean, and here I will pass on the first column, the entire first column, the entire first predictor column, which is represented by x of I, or the ith column. For the very first iteration it will be x of 0. For the second iteration it will be x of 1, which will be second column, and so on. And then to collect the standard deviation value for the ith column, which is for the very first iteration it will be x of 0, and we'll compute the standard deviation for entire column. Whatever value you get, you will add that to your std list. So let us come outside the for loop. So for returning the normalized data I can say return np.array x of I minus mean I, and divide that with the standard deviation stdi. Here we will be using list comprehension. So for I in range 0, 4, and then I can pass on the numpy array for our response variable, mean, and the standard deviation that we just computed. Else if we don't want our input data to be normalized, I can say return numpy array x and numpy array of our response variables y. So now let us test our read data function to see what we get. So I can say x, y, mean, and standard deviation. So we are expecting these 4 values if we want our data normalization to occur, and we do want that our input data should get normalized. So we expect to get these 4 values, and let us invoke our read data function, pass on the file path, which is iris.csv, and here NOC is 5 by default, so I'm not going to pass any value. And then let us print x, y, mean, and standard deviation to the terminal and run the file by saying python knn.py. Okay, so we have collected our predictors collection. So we have the first predictor column, and this is normalized. You can see we are getting negative values as well, and these are 150 such values for the first predictor. Then we have the second predictor, 150 such values for the second predictor column. Then the third predictor column starts here, and finally the fourth predictor column. Then we have the response variable collection. So we are getting all these categories in our y variable. So this is our y variable, which is a list, and we have 150 such categories, and most of them are repeated, as you can see. So we are having 3 categories spread over 150 values. And then we have the mean values. So this is the mean for the first column, or your first predictor column. This is the mean for your second predictor column, the third predictor column, the fourth predictor column, and the standard deviation for them respectively. So now currently our x is of the form a list of lists where each list represents all values of input variables. So the first list inside our X will be all values of input variable 1. Then the second list will be all values of input variable 2. Then the all values of input variable 3 and all values of input variable 4. But what we want is, we want all values of input variables. For training data points, we want that the first list should represent a point. That is, it should be a list of points, and where each point is represented by a list, and it should have all the values of input variable for that point. So for that, we can easily take on the transpose of the matrix that we get, which is X, and the rows of X will become columns, and the columns of X will become rows. So for that, we can just take the transpose of our predictors collection. So I can say X np dot transpose, pass on the X variable. Now in a given dataset, all the rows of iris setosa are first 50 rows, as you can see here. So all these 50 rows are for iris setosa. Then starting from the row number 51, we have iris versicolor, and this goes on till 100, and the last 50 are for iris virginica. Now this makes it difficult for us to select one part of the dataset for training our model, another part to evaluate the statistical power of prediction of our model on the training set. Now in order to tackle this, what I can do is I can shuffle the original dataset randomly using the random order function that I will define in just a minute. Random ordering and shuffling of our dataset. So I can say random order, and this will take on X and Y and will return us X and Y which are randomized and shuffled. So let us go right above and define our random order function. So right here, let us define the random order function that will take on our predictors collection. And the list of response variables, which is Y. And then let us create an ordered sequence up to the length of the rows that are there in the dataset. So I can say np dot arrange, and here we will pass on the stop point. So till where we want to make an ordered sequence. So I'll give the shape of our dataset, which is the number of rows that are there in our dataset, which is represented by x dot shape 0, and this gives us the ordered sequence, and I will pass the number of rows, which is this, into it, and let us store that in a variable, and I will name it as randomize. Now let us shuffle the above list that we get by saying np.random.shuffle and pass on the randomize variable. Now to shuffle our predictors collection and the list of response variables, I can say X and pass on the randomize variable to it, and Y randomize, and let us return XY as a list like this. Now let us come down. Now before making our predictions, let us perform the splitting of our dataset into the training and testing portions respectively. So first I will define a variable and I will name it as splitting ratio. Splitting our dataset, splitting ratio, set that to 0.8, and this ratio determines the value of how much data do you want to use as the training data set. This is the row at which we split our dataset as training and testing. Now ratio is the value of how much data you want to use as your training portion. Next, let us define a variable and I will name it as row where split occurred, and here we want the row which should be an integer, and I can give the number of rows of our dataset which is represented by x dot shape 0, and then we'll multiply that number with the splitting ratio, and this will give us the row where the split should occur. You can change this ratio and automatically the change will get reflected here, so you'll get a different row where the split will occur. But for our dataset, I'm using the splitting ratio as 0.8 because I want that 80% of our dataset should go for training and 20% of our dataset should go for testing. So now we have the row where the split occurred. Let us store our predictors collection for training in a variable, and I will name it as train_x. So training data train_x, and we'll collect all the predictors for all the rows till the split row in our dataset. So with this split, we will have 120 rows or data points in our training dataset. So let me show you how we will have 120 rows. We know that we are having 150 rows in our dataset. So if our split ratio is 80%, which is 0.8 as a fraction, I will multiply that with 150, and this gives us 120. So 120 rows in our training dataset, and the remaining ones, which is 30 rows, in our testing dataset. Right. So creating our training dataset portion, I can say, so from our predictors collection, starting from the very first row until the row where the split occurred, and this is exclusive, so we are collecting all the predictors for all the data points till the split row. And let us do the same thing for our list of response variables. So we will collect the response variables till the split row for our training dataset portion. So I can say train_y, and starting from the very first row till the row where the split occurred, and this is exclusive. Now to create our testing dataset portion, I can collect all the predictors and the response variables starting from the split row itself till the last row of our dataset. So I can say testing data test_x starting from the row where the split occurred till the end. So here we will not specify the end index, we'll omit that, and this means we are going till the end row of the dataset. And let us copy this down below and change this to y. So starting from the row where the split occurred till the end row, we'll collect all our response variables in test_y. So now our splitting of the entire dataset is done into the training and testing dataset portions. Let us make the predictions on our testing dataset. So let us first define our k hyperparameter, which is the number of nearest neighbors that we want to take into account for making our predictions. So the nearest neighbors hyperparameter k, and set that to 10. And now let us define a list of predictions where we will store the prediction for our testing data points. So I can say predictions for the testing dataset portion, predictions, set that to an empty list. Now for all the rows that are present in our testing dataset portion, let us make use of the k nearest neighbors algorithm, for which I will define a function in just a minute to predict the class to which that particular point in our testing dataset should belong to. So I'll use a for loop for index in range 0, test_x dot shape. So for all the predictors of all our points in our testing dataset, we want to find the k top nearest neighbors for the unknown point. So k top classes, and set that to an empty list. Now in order to get the top k Euclidean distances, so Euclidean distance is a metric that I had discussed in the video of KNN intuition. The link for that video can be found at the top right corner of this video. So we can invoke the KNN function that I will define in just a minute, and we can pass on the collection of predictors like this. So train_x, collection of predictors for training set, and the response variables for our training set. So train_y, then the current point that is under test. So we can get the current point by using the index that we are currently on, and we can say test_x and use the index to get the current test point. And we can also pass on the value of k which is the number of nearest neighbors that we are using for the algorithm, which in this case is 10. And this should give us the k top values. So now let us define our KNN function. So let us go right above. Right here, I will define the prediction method using the k nearest neighbors algorithm. So def KNN, and this will take on our training data and the new data point or the new testing data point and the k value. Now let us define a list of Euclidean distances for each of the categories, and I will set that to an empty list for now. So Euclidean distances with category. So we have 3 categories: iris setosa, iris versicolor, and iris virginica. Set that to an empty list, and let us extract the predictors collection for our training data. So I can say train underscore x, set that to training data, and it will be the first element of the list that we are getting here. As you can see, this is a list, so we will destructure this out, and we are collecting it right here. And then we can extract the list of response variables for our training data, which is the second element of our list, training data 1, which represents the second value of our training data list. So now we are getting both the predictors collection and the list of response variables. Now let us calculate the Euclidean distance between the unknown data point, which in this case is new data point, and all the data points in our training data. So now to calculate the Euclidean distance between the unknown point and all the data points in our training data set portion, I can say for index n, range 0, and the training dataset portion and the length of that. Okay, so we are having the predictors for each of our rows in the training dataset, and we are taking all the predictors. We are iterating over the predictors of the training dataset portion, and then we will compute the Euclidean distance between the point represented by these predictors that belong to a certain point. So each time we will grab all the predictors of a certain point by using this index, and we will compute the Euclidean distance of that point to this new data point. And we will do that for each of the points that are there in our training dataset. And we are considering only the predictors for each of our rows of the training dataset. So I can say Euclidean distances with category dot append, and here I will say Euclidean distance. So I will define the Euclidean distance function in just a minute, and this will take on the list of predictors for a certain point, which we can refer using train underscore x index. So this will give us the list of predictors for the current point, and you will compute its shortest distance with new data point, that is the current point under test, and then I will pass on the current response variable, so train underscore y, the response variable at the current index. So now before proceeding further, first let us define our Euclidean distance function. So let us go right above. So right here let us define the Euclidean distance function, which we will use to compute the distance between 2 points. So if we have 2 data points a and b in a 2-dimensional space, the Euclidean distance gives us the shortest distance between a and b. So I can say function to compute the Euclidean distance between 2 points a and b. So def Euclidean distance, and this will receive 2 points as arguments. And now let us define a variable, and I will name it as distance and set that to 0.0. Now for each of your points a and b, I can grab the corresponding predictor values for each of these 2 points, namely sepal length, sepal width, petal length, and petal width, and then compute the square of differences between them. So I'll make use of a for loop, and I can say for I in range 0, length of A, and then for the point A, I can grab each of its predictors and compute the difference between the corresponding predictors of B with respect to it. So I can update my distance and say distance as distance plus A of I minus B of I, that is the difference between corresponding predictors, and raise that to the power of 2. Now whatever value we get as our Euclidean distance, let us compute the square root of that and then return the final value from this function. So return np.sqrt, which is the square root of the distance that we got. So now back in our KNN function, let us print the Euclidean distances with category to the terminal and examine what we get. So right here I will print Euclidean distances with category, and for now let us eliminate this and run the file. Now whatever Euclidean distances between all the data points in our training data and the unknown point that we get, let us sort them in increasing order. So this is the output that we are getting. Let us sort this out. So right here let us comment this out, and I will say Euclidean distances with category dot sort. So here we can use the sort method that Python provides us on the list of Euclidean distances with category. Now from this sorted collection that we get, let us return the top k Euclidean distances. Now these top k data points or Euclidean distances represent the k data points which are nearest to our unknown data point, and depending on their classes, we will assign a class to the unknown data point. So right here I will return Euclidean distances with category, and I will return the top k values like this. So starting from the index 0 and till the index k, but the index k will be exclusive, and we can even omit this 0. So now let us go down below and let us collect whatever we get back from our KNN function in our variable k top values, and then we can print the k top values to the terminal, and let us run the file. So now let us comment this out. Now out of the k nearest top data points that we just got, we now have to find out which class is the most occurring in those data points and then assign that class to the current testing data point. So let us make a loop that will run for k times, and then what we need to do is, and then we need to collect the second value which represents the category for our analysis. So I can say k top classes dot append k top classes. So now to refer this element, I can say k top classes I, and then to get this second value for each of our lists that we are having, I can say 1. So for each of the k top values that we get, we'll grab the second component of each such value, because as you can see, k top values is a list of lists where each list represents the Euclidean distance value and the category. So we are just grabbing out all the categories, which is the second component of all the lists that we are having in k top classes list, okay, and we are appending them to the k top classes. So now let us print the k top classes list to the terminal and run the file. So print k top classes. Okay, so I made a typo. It is k top values. Okay, and again run the file. So now you can see we are getting the k top classes. So these are our k top classes. So now let us comment this out. Now to get the most frequent occurring class, we can make use of the mode concept on our k top classes to get the class to which our testing data point should go. So right outside our for loop, I can say predictions dot append, and I will use the mode method on the stats functionality, and I will say k top values, not values, k top classes, and 0 0. So now let us finally print the list of predictions that we get to the terminal. So print predictions and let us run the file. So this is the result for each of our 30 test data points, the classes to which they should get assigned. So this was all about the video on implementation of the KNN algorithm from scratch on the iris dataset. So in the next video, we'll start with a new classification algorithm, and that is the naive Bayes algorithm. So if you like the video, do give it a thumbs up, subscribe to the channel, hit the bell icon to get the notification for all the upcoming uploads, and I will see you guys in the very next one.